Do you know how to model a sandwich plate under explosive loading using blast analysis in ABAQUS? If you are into engineering or simply fascinated by how things hold up under intense pressure, this video is for you. In this tutorial, I will guide you through the 3D modeling of a steel sandwich plate facing an air blast explosion using ABAQUS. You will learn how to set up the model, apply explosive forces, and analyze the results. This isn't just cool to watch, it has real-world engineering applications.
Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life.
In today's tutorial, I'm going to model steel sandwich plate under explosive loading. Explosion is happening at the center of the plate, and I'm going to model the quarter-symmetric model of this plate. And you will see in a minute how do you model this plate and how do you interpret results. The learning outcomes will be that you will go away and do actual modeling yourself after following the steps which I'm going to teach you today. The example is taken from this book. The dimensions of the plate are 1.2 meter by 1.2 meter and it is 60 millimeter deep. Our objective here is to study the response of sandwich panel to explosion force and also to investigate the energy variation and applied strain rate on the sandwich panel. The explosive loading is 0.5 kg TNT of mass, which is placed at a height of 100 millimeter from the center of upper plate. These are the material properties: density, Young's modulus as usual for steel members, Poisson's ratio is 0.3. Here I'm going to use damping as well. In dynamic analysis, every structure has got damping and I will use Rayleigh damping, and alpha is 50 and beta is 0. For these kind of materials, the strain-dependent plasticity model should be used and ductile damage should be used. And there is Excel file for that. I will use this Excel file and I will attach this for your convenience in description down below. I will be using SI units to model this problem. I will be using these 9 steps to model the problem, starting from part property, assembly, step, interaction, load, mesh, job, and visualization module. The lecture slides and modeling files are included in tinyurl.com/jqureshiabacus, and you can watch full playlist at tinyurl.com/jqabacus. Let us now dive into the problem. To start modeling, I will start with ABAQUS Standard. Click on ABAQUS Standard. First, I'm going to model the plate. Double click on part and say plate, and it is 3D deformable solid extrusion, and approximate size is going to be 2 because I will be using meter units here. First, I will start with rectangle and pick any rectangle, draw the rectangle, press right mouse button and cancel the procedure, and then use dimension. This is 0.6, 0.6 again, and then click on this icon to auto fit. Once geometry has been created, I will click on cancel button to cancel dimension, and I will click done. Its depth is 0.01. Click OK to complete the plate. Then I will create a stiffener. Double click on parts and say stiffener. It is 3D deformable shell and extrusion. Again, I will use the same size over here. So first I will create a line, a vertical line. Once line has been created, then I will add dimension. It's 0.6. Dimension has been added. And then I will create a linear pattern. So click on linear pattern and click on here, click done. The spacing will be 0.06, and I would like 9 elements in this direction. Now you can see 9 elements have been created, and then I will create a horizontal line, another stiffener here. Then I will give the horizontal dimension and vertical dimension. So click on dimension. It is vertically, it is 0.06 meters away from top. So I will click on this one, click on this one here. The important thing to note here is that when you are dimensioning it, take the first point as the starting point. In that way, it will move this line. Otherwise, it will move this vertical line, which will not make sense. And then horizontally, I will have a distance between here and this line as 0.06 as well. So once this is done, then I will dimension this line as well. This line is about 0.6. So dimension the line as 0.6. And then I will create a linear pattern for horizontal line as well. So click on linear pattern, click on line, and not this one, the other direction. In other direction, I will have 0.06 in the same way, not upwards. I would like it to be downward. So I will just flip the direction, and then 9 elements have been created. Once it's done, I will simply say done, and it will ask me for depth. The total depth is 0.06, and depth of the top plate is 0.01. Depth of the bottom plate is going to be 0.01. So depth of a stiffener is going to be 0.04. Remember that I'm using meter units. In this way, we have created part for stiffener as well. The next is property module, where I will define materials and assign properties. Double click on material and say steel. And here, firstly, I will define the density. Density is 7850. And then I will define damping. For damping, alpha is 50, other elements are 0. And then I will define elastic properties. Elasticity, I have 200 e raised 9 gigapascal. Poisson's ratio is 0.3. Elastic property has been defined. Then I will define plastic properties and plastic. And here I will use strain rate dependent data. So what it will do, it will add this third column to the table. And then I will copy data from here, copy, and simply I will paste it here. Once I've done it, then I will define ductile damage as well. Fracture strain, stress triaxiality, and strain rate. These are the properties which should be obtained from experiments, but here I have taken these properties from the book. So click on these properties, simply copy them, and then paste them here. Once this is done, then all properties are defined. Click OK, material has been defined. Then I will define the sections. So first section is plate underscore sec, and I will define solid homogeneous section for plate. The next one is stiffener section, and that will be solid homogeneous, and the shell thickness is 0.001. And I will keep all other things as default. Material is steel. After this, I will assign these sections. So go to plate, section assignment, choose this, click done, and then assign plate section. And then go to stiffener, double click on section assignment, choose the entire bit, and assign a stiffener section. And I will say offset is from middle of the section. Click OK. This part has been done. Then I will click on assembly module. Click here and then shift, add both of these parts. And then I'm going to move a stiffener on top of here. For this, I will create a datum point. Click on datum, offset from point, offset from this point, and in X direction, it is 0.06. Once this is done, then I will move this instance on here. Click on instance, translate, then choose this instance stiffener, And start point of translation, I will simply click on this point. End point is this one. So this is okay. This is my top plate, and I still need bottom plate. So for bottom plate, again, I will click on linear pattern. Then I will select the instance, and I don't want anything in this direction, but I would like to, and I will choose the direction. You can choose X, Y, and Z direction. X and Y directions are chosen automatically, but if you wanted a different direction, then click on this button. I will choose the Z direction, and I will click on this part of the stiffener and 0.05. The reason I'm having 0.05 is that I'm starting from here. The total thickness of the entire sandwich panel is 0.06. And then I'll reverse the direction. Now you can see that I've been able to assemble the quarter symmetric model. Once assembly is done, then I will move to step, click on a step, and here I will define dynamic explicit step. Click OK. I will turn on nonlinear geometry, and the step is 0.1. It means 0.1 second. The load will be applied suddenly. Explosion will happen suddenly. Then I will move to interaction. Firstly, I will define the explosion. But for defining explosion, I need a point which is 100 meters away from here. So I will go to tools and define a datum first, and then offset from point. Offset, I will choose this corner, and in Z direction, I want it at 100 millimeter, means 0.1. The datum point has been defined, and then I will define a reference point at that point. Go to reference point, click here, reference point has been defined. Now I will define interaction in the three ways. One is I will define the explosive loading. Other is I will define a self-contact between the elements, because when explosion will happen, the stiffener might fold over each other, so there should be self-contact. And thirdly, I will attach the top and bottom plate with stiffener, and I will tie them up. So three interactions. So let's double click on interaction first. First is explosion, and I will click on incident wave, click continue, select a reference point. So it's asking me for a reference point. I will select this reference point, and then I will use this cone web blast. It is asking me to select the surface. It is going to touch this top surface, and I will click continue. And over here it's asking me for wave property, and I will create property here. So click on property and say explosive loading. And here I will click on incident wave, click continue, and definition will be air blast, and TNT is 0.5 kg. Now here there is a mismatch in the book. At one point, the book says it should be 0.5 kg. At other point, it applies 1.5 kg. So I will leave it to you to decide. In my view, with I have done both. With 1.5, it is giving the right results, and that are comparable with the book. But here, I mean, to be consistent, I will simply apply 0.5. Now I'll keep everything as default. Explosive loading, I've already created the property. Here it is 0. Magnitude of scale factor is 1. Explosive loading has been applied. The next thing, I will apply a self-contact. So self-contact, and that will ensure that, click on self-contact. So I will define general contact and all with self. And interaction property, I will define interaction property as friction, and that property will be a contact property, friction, continue. And here, mechanical tangential behavior, I will use penalty formulation, and coefficient of friction is 0.35. And then click OK. Click on friction and then click all right. The general contact has been defined. And next, I will define constraints, tie constraints. So I will tie plate and P and S. Click continue. It will ask me for surfaces. I will use the bottom surface of each plate. I will press shift button and choose the other surface. Click done. And then I will use node region. I want to tie up all the node region, and in node region, I will choose entire stiffener. So if I see isometric view, and here I will keep everything as default. Now this has tied the stiffener with the plate. Once this is done, then I will go to load module where I will define the boundary conditions. Now this part is symmetric because this is a quarter symmetric model along Y, and this part is symmetric along X, and the bottom parts are fixed. So first I will define these sets. I will go to assembly and sets. That will make things easier for me when I will define the boundary conditions. So go to assembly and go to sets, and first define a fixed set. For defining a fixed set, I will go to XY view, and these surfaces, they should be tied. And first I will choose everything, and then I will press Control key on keyboard, and then I will unselect these bits. In that way, it has only chosen the areas where I want to apply fixed constraint. This is quite efficient way to apply boundary conditions. Otherwise, you will have to choose them individually, in which you can make a mistake. So if I go to 3D and if I go to perspective view, you can see that this was the area I wanted to apply fixed conditions. And then click done. I've done fixed. Now I will do Y symmetric. Y symmetric is this surface. Again, I will go to XY plane and I will choose, I'll double click on set and I will choose Y symmetric. Click continue. And here, first I will choose everything. Then I will deselect this reference point. I will deselect these points as well. And then I want to have a look at 3D view to see that I've chosen the right things. Yes, definitely. So this is Y symmetric. And in the same way, I will choose X symmetric as well. So click on here, X symmetric, continue. First, I will choose everything and then control button and unselect this reference point and unselect these values. And finally, have a look at the three-dimensional view to see that you have chosen the right surfaces. Click OK. Once this is done, then it's easier for me to apply boundary conditions. So double click on boundary and first of all say fix symmetry in caster. It should be applied in step 1. And here it's asking me for surfaces. I will click on surface, choose fix, highlight the surface, continue, and it is in caster. Next, I will define Y symmetric, double click Y sim, and again, symmetry, anti-symmetry, click continue, choose Y symmetric, continue, and here click on Y symmetric, continue. This boundary condition has been defined. Then again, X symmetric, symmetry, anti-symmetry, and choose X symmetric, click continue, and choose X symmetric from here as well. Now boundary condition has been defined. Then I will go to mesh. And I would like to mesh in part. First, I will mesh plate. First, I will click on assign mesh controls. I want a structured hexagonal mesh. And then I will assign the element type. Choose this entire surface. Elements, make sure that you choose explicit elements. Otherwise, this is not going to work. So three-dimensional brick elements, explicit elements, click continue. Then click on seed parts. The size of elements is 0.005. Click apply. The reason for having this 0.005 is that because this is 0.01. So I wanted at least one element across the thickness. In that way, it will capture the right behavior, the actual behavior of the structure. And then simply I will mesh the part. Part has been meshed. Then I will move to stiffener. Again, first thing I will assign mesh controls. Click on it. Here it is saying free. I don't want free. I would like quadrilateral elements. I would like the structured elements, and click continue. And then I will assign element type. Again, choose this and element type. Make sure that element library is explicit. S4R shell elements. Click OK. And then seed part. I'm using 0.005. The reason for using 0.005 is that the depth of the shell element is 0.04. It will at least ensure that there are 8 elements. If you divide 0.04 by 0.005, you'll get 8 elements. Apply, and then simply mesh the part. Yes, part has been meshed. And if you have a closer look, you will see that 1, 2, 3, 4, 5, 6, 7, 8. I have 8 elements over here. Once this is done, then I will go to job module and define the job. Here I will say explosion and continue. And here I will keep everything as default, except that in parallelization, I will use 2 processors. It will make the analysis quicker here. And then OK. Now here I would like to save the file and set working directory as well. And now it's ready for analysis. I will submit the analysis. If everything is fine, then it will let me submit. If it isn't, then certainly I've made a mistake somewhere. It is a very heavy analysis. It's going to take a lot of time. I've already carried out analysis of this problem in a separate file, so I'm going to show you the results. So this is the problem. If you can see that this is failing, you can run the movie to see. You can have a look at the PEEQ plastic strain, which will tell what's happening with the elements, what is failing. As you can observe that stiffeners are failing, but I can't see it really properly, so I would remove the top plate. I'll stop it and I'll click here and highlight in viewport. I will remove this plate, and now you can have a closer look to see that these elements are failing over here because plastic strain has reached, and you can see there is a kind of warping and buckling of these stiffener elements. I will bring the plate back. I think it was this plate. I will find the displacement, ODB output, unique nodal. Here I'm interested in displacement in U3 direction, and I will choose the node, just the corner node. I will plot it and I will save it as well. Now you can see that the displacement is about 0.035, but in the book it's about 0.07. The reason is that I think 1.5 kg of TNT is applied, which you can see over here, but earlier they said 0.5, so I think that is the reason. So here you can see equivalent mass of TNT is 1.5, but initially at start of the book they say it is 0.5 kg TNT. So I've used 0.5 kg. If you use 1.5, you'll get the same results as you are getting over here. And then they have plotted the plastic dissipation and strain energy. Let's plot these as well. Double click here, history output, continue. I would like to see the plastic dissipation energy. You can see it's about 7 into 10 raised 3 kilojoules, and it's certainly less than the book value, but if you apply 1.5 kg of TNT, you will get the same value. Strain energy, again, this is strain energy. Now, the key thing to remember here is that you need to have actual material properties and you need to understand the material properties. How did we obtain these properties? And also, this kind of problem should be validated against experiments. But because I couldn't find quickly experiments, so that's why I thought to share what I've learned so far. Thanks for watching. Don't forget to subscribe for more practical insights into structural engineering and beyond. Until next time, stay curious.